on to talking about machines or work easier for us. Examples things can range anywhere from cars, nails, scissors, wrenches, tire irons, staplers, screws. There's so many different things that going from really simple to really complex that all help us make our work easier for us. Start talking about, and we'll talk about types of machines in the next note set. Before we get into some details, we need to know about the work we put in and the work we put out. So there are always two kinds of work that are involved when you have a machine that is used. The work that is done on the machine to make that machine work, and the work that the machine does on another object. So for example, if you are opening a can of paint with a screwdriver, you kind of have to pry the lid off of a paint can. You are doing work on the screwdriver, which in this case is the machine. So you're doing work on the screwdriver by pushing it down, and then the screwdriver does work on the paint can lid by lifting it up. So you're putting work into the machine, which is the screwdriver, which then puts work out to the paint can lid. So the work input is the work that you do on the machine. The input force is the force that you apply to the machine to make it move. So in the case of the paint can and the screwdriver, the work input is the work that we did on the screwdriver. The input force is us pushing down on that screwdriver. The work output is the work that's then done by the machine. So the output force is the force that that screwdriver would put on the paint can lid in our example here. So we always have a work input and a work output. If you think about it, to make a machine work, you always have to do some kind of work, whether it's, in some cases it's pushing a button, some cases actually putting in some force like with the screwdriver and the paint can lid, but there's always some kind of input and then it will result in output. But one golden rule to always remember is that work output can never be greater than work input. Remember how we talked about in chemistry the law of conservation of mass. There's also a law that's called the law of conservation of energy. Now, you cannot magically get energy out of thin air. You cannot have energy magically disappear. It can be transformed into different types, but you're not able to get more energy out of a machine and more work out of a machine than you put in. So if you were to put in 100 joules of work, you could, if it was a perfect machine, get out 100 joules of work, but you can't magically make more work than what you put in. So output is never greater than input. Don't lessen the work that they do, they just make it easier. So if you have to do 100 joules of work to get, get an object to move, if you have a machine to help you with that, it's not going to lessen the work. It's not going to be any less than 100 joules. It's just going to make that easier by changing the size of the input force and also possibly changing the direction of that force, or maybe both. So if you think about if you have a truck bed and you're trying to lift something into it, which would be easier? If you just lifted it, if it's something really heavy, or if you had a ramp to push it up. Now, I'm assuming that you were thinking ramp. So, the reason this is because a ramp is a machine. A ramp helps make that work more easy. The person lifting, and again, I don't know why my pen's not working, but I would draw this for you, but the person lifting up the load, or whatever the case is that's going into the truck, has to put more input force in, but it's over a short distance. So that work is going to calculate, you're going to have a large force, but a small distance to calculate out work. Well, if you have it on a ramp, you're going to lessen the force, but you're going to increase the distance. So you're still going to come out to have the same amount of work. It's just going to be easier. What we call the force distance trade-off. You either increase the force or increase the distance, but not together. As one increases, the other has to decrease. So if you have a wheelbarrow. You have to, the wheelbarrow is going to increase the force over a shorter distance. So it requires more force for the wheelbarrow, but you're moving it over a shorter distance, which then makes the work easier. If you're hammering a nail, you have to put in less force than, if you were just trying to try to hit a nail with your hand, you have to put in less force with a hammer, but it's doing the work over a longer distance. You have to swing that hammer. So again, it's still the same amount of work, it's just making it easier. A pulley changes the direction of the force. So if you think about like a wishing well kind of fountain with or a well where you pull the bucket, that's a pulley. We'll get to that next slideshow, but it's lengthening the distance, but you have to do a lot less force to pull that up compared to if you just had a bucket on a rope, you'd have to put in a lot more force to pull it. We just talked about the paint can and the screwdriver. It's changing the direction of the force and the amount of force you have to put on there. So all of these things are not lessening the work. You're just trading off, do I need more force? Do I need more distance to make this easier? Regulations here. One is mechanical advantage. So what this tells us is how many times the machine multiplies the force. So we're comparing input force to output force essentially. So the equation for this, which again you may want to write on your equation sheet right now, is mechanical advantage equals output force divided by input force. So if the machine is only changing the direction of the force, its mechanical advantage would be 1. So if it's not changing the output force or input force, it's going to automatically have a mechanical advantage of 1. Some machines are going to have an advantage of less than 1 because you're exerting the force over a longer distance, but you're never going to have a mechanical advantage of over 1 because remember, our output cannot be larger than our input. It's very similar. It's just tells us something a little bit different. But it's how efficient the machine is. So mechanical efficiency. So because of the work done by the machine is used to overcome the friction created by the machine, machines are not completely efficient. Remember, friction ruins everything. Friction is the reason we cannot see Newton's first law completely. Friction is the reason. Friction is there all the time, so there's reasons that we can't. There's lots of, well, obviously it's a good thing, but lots of things that we cannot do or view because friction doesn't go away. Same thing for machines. As parts rub together in a machine, whether it's a complex machine or it's just something as simple as a screwdriver, when the parts touch, there's going to be friction, which means some of that energy is going to friction and the heat energy that comes from friction, and not all of it can go towards that output. So we're looking at how much output do you get with the input that you put in. So to calculate this, we take work output divided by work input, just like the last one, but then we multiply it by 100 because we're finding this as a percent. So it's going to be anywhere from 1 to 99% efficient. The higher the efficiency means the less friction. So if you make it so there's less friction, you're going to have a more efficient machine. It is impossible to have 100% efficiency. Why? Because we always have friction. We should hopefully get this through our heads by now. But if we did have something like that, it'd be called an ideal machine because we would have just as much work going out as we'd had going in.